potent type of a compound. But we're not going to go through it in any detail. But just so if you're in a casual conversation also with your friends, you can talk about these diazonium compounds. And basically what this is we can take an aromatic amine, like aniline, this compound here, and react this with HCl plus NaNO2. And this whole species here makes something that's known as HONO, which is nitrous acid. And what this does is it makes a compound that looks like this. It's two nitrogens, where this has a positive charge. And this is known as a diazonium compound. So if you're interested in the mechanism of this formation, I encourage you to take a look at it in the textbook. It's not going to be on our exam, but there's a lot of proton transfers that are involved, but it would make sense as to how this is actually formed. Why this is so useful is that these diazonium compounds can be used in what's known as the Sandmeyer reaction. What you can do is you make a diazonium compound and react this with, this looks kind of strange, but we'll say KX Cu2X2. It starts to look like algebra. And this will introduce X at this particular position. And X equals, oftentimes, there's lots of different groups, such as, some of them are chloro, bromo, or things like cyano, like CN. So for example, if you have a benzene ring, and you turn it to a diazonium compound, or the amine, I should say, to the diazonium compound, and then you take potassium chloride, copper chloride, you can introduce a chloro substituent. So this is, as I mentioned, very, very useful. And one other one is you can take a diazonium compound and treat this with water and heat, and then some sort of usually a salt. Let's erase this. Like the conjugate base of sulfuric acid as a salt. And what this is going to make is a phenol. And this is a way of introducing a hydroxyl group. So I know this is kind of a bunch of letters and a mysterious reaction overall. This reaction as well might have some radical component to it, but you can make these diazonium compounds. I just want us to be aware of it. And then we can turn these diazonium compounds into a variety of other groups. So we can introduce a halogen, like the chloro group, or you could use potassium bromide, copper bromide to make the bromo. There's ways of introducing a fluoro and an iodo as well. A cyano, that was our CN, or nitrile. Or we can use this to introduce a hydroxyl group to make phenol. So very useful reaction in that respect. These diazonium compounds are very useful when this is a benzene ring, when it's an aryl. If you have just an alkyl group here, though, they're quite explosive, so they're not always the easiest to work with. Okay, so I know that's a little out of place, but something to mention. Yeah, about reactions left and right, and so a lot of them. I know it's a lot of material, and oops. So then, how about two more reactions? And this will be the last thing with the aromatic compounds. Up to this point, we've been talking about all of this electrophilic aromatic substitution, where the benzene ring, I'll put it down here, was reacting with our strong electrophile. So notice here, the benzene ring is the nucleophile, and this of course is the electrophile. I try to abbreviate electrophile. Don't say nuke for nucleophile. Now, let's have another observation. If I can scroll up, I'll get rid of this Sandmeyer reaction. Now what we want to consider with something that's known as nucleophilic aromatic substitution. And the observation would be, let's say we have this aromatic system with a chloro and 2 nitro groups on it. If you were to react this with a strong base like sodium hydroxide, there would be water around, and then second, treat it with an acid, we actually would end up with a substitution reaction where the nitro groups are still there intact, but that chloro substituent has been replaced or substituted with a hydroxyl plus sodium chloride. So now we need to come up with an explanation for how this reaction might occur. Now we know that the hydroxyl group cannot just attack here in an SN2 reaction and kick out the chloride, so where this would attack and the chloride would leave all in one step, because SN2 reactions are unfavorable at this sp2 hybridized carbon. We also know that this is not going to take off and form a carbocation, an SN1 like reaction, because that's unfavorable. But now the problem is hydroxide here. Sodium hydroxide is a strong nucleophile. All the reactions we've seen up to date, the group that's over here is the electrophile. So something seems to be different here. And this is the case now where we're dealing with, we're flipping the nucleophile and electrophile around and considering this nucleophilic aromatic substitution. And there's 2 general mechanisms. And this was kind of highlighted in that video as well. So there's addition-elimination, and then what's known as elimination-addition. This is also known as a substitution nucleophilic aromatic reaction. So SN1, SN2 were 2 previous substitution mechanisms. This is another one, SNAR. So a potential mechanism for this is that maybe this does actually act as a nucleophile of hydroxide, but not in an SN2 reaction, but in a way to then destroy aromaticity. So let's move these electrons out from that double bond onto that carbon. And that's going to give us, I'll draw it down here, an intermediate where we have chlorine, chloro, OH, and now we've broken our aromaticity. So now we've paid an energetic cost. However, just like what we saw with our previous reactions, maybe there's something here that can help stabilize this. So we can actually draw resonance structures. Remove these electrons here, and move these electrons onto this carbon. So all this stuff is the same. Oops. And now what we've done is remove this here. Now we have a lone pair of electrons here. Actually, I'll put them on the inside. I think it's easier to see. We can draw another resonance structure. We continue to move these electrons here, and then onto, I guess I'll put it on the inside again, this carbon. Whoops. Nitro, chlorohydroxyl here, lone pair. Now, these nitro groups here are serving 2 purposes. And as I mentioned in the video, I won't write it here, is that you need to have electron withdrawing groups for this reaction to occur on the benzene ring, and they need to be at the ortho and or para position relative to the chloro. And the reason for that is that they are pulling electron density away from the ring, making it much more electrophilic, it being the benzene ring. However, when the nitro groups are also at the ortho or para position to the chloro, they can directly participate in resonance. So I'm going to erase this from my notes and link the nitro group here. Draw it out. And now if they have this lone pair of electrons, let's make this a little larger to see. This is a little more clear. Here, the nitro group can actually participate in resonance. So we could draw a resonance structure, remove these electrons here, and these electrons out into this oxygen. So that would give us a resonance structure that looks like this. So the nitro group is actually participating in resonance stabilization. And you could write the same thing for this one here. So let's just put it here. Okay, so that's our, it's kind of messy the way it's drawn, this is our resonance hybrid. So this is unfavorable, forming this negatively charged species. We're breaking aromaticity, but we have resonance stabilization. So this is, it's all resonance stabilized. And this is known as the Meisenheimer complex. Okay, so now we're not quite to our final product yet. So we generated this resonance stabilized intermediate. We've shown that the nitro group can participate directly in resonance stabilization. But now what we need to do is we need to kick out the leaving group. So why don't I just go down here and then I'll redraw. So we're going to expel the leaving group or kick out the leaving group. I'll redraw the first resonance structure just to make it a little more clear, hopefully. It's not really drawing it well, but we have the nitro here. Our lone pair of electrons just showing one of the many resonance structures. Now what we're going to do is we paid this energetic cost breaking aromaticity. We're going to get that energy back, kicking out our good leaving group. Restored aromaticity. And we have generated this, plus we lost our chloride. And we started off with sodium hydroxide, so we end up with sodium chloride. So this is a new reaction at an aromatic center. We've flipped around the electrophile and nucleophile from the previous reactions, and so the hydroxide is acting as our nucleophile. It's attacking the aromatic ring, which has these electron withdrawing groups, in this case at both the ortho and the para position relative to the chloral leaving group. This is energetically costly as we're breaking aromaticity. Now we're forming an intermediate that has a negative formal charge, not positive like before, but now negative. But we can actually draw resonance structures that stabilize this structure. And these electron withdrawing groups you need something at either ortho or para or both, as I mentioned. And the reason for that is that they participate in resonance stabilization as well, which is the nitro group here on the right. And this mechanism is known as addition elimination because the hydroxyl group is first adding, generates the Meisenheimer complex, and then we eliminate chloride down here in the very bottom to restore the aromaticity. Okay, so that's a new reaction.